Hi, and welcome to another Octagon plant video. In this video, we're going to take off where we left off on the last one. So here we have the tank valve, and obviously if I push the button, this will actually come out. And the grand unveiling for this video is, ta-da, the actual tank itself. So since the last video, I've had a chance to basically print the second version of the design, which is actually the one down here. We'll go through that throughout this video, but obviously the actual main tank body itself. So if somebody looks at these videos, I guess in chronological order, somebody might say, where are we going to? I guess, seeing this, hopefully we'll start to put some pieces together. And Octagon is simply the name of the company under which all of this is being done. And when I say plant, obviously a tank is part of the equipment that is going to be built in a series of mini plants, but more on that, I guess, in another format and or in other videos. Eventually we're going to see that 3D printing is an interesting development, but overall, and we can see it here actually, why is everybody so crazily buying 3D printers and going crazy printing a whole bunch of stuff? Well, it's because metal was invented before plastics, effectively, and everything is made of metal, and plastics are obviously weaker. And it's abundantly evident in all of this. If you look at this, we have a tank, which could be very simply a pressure tank for compressed air or to fill up a car tire, or whatever the case may be. And here we have a quick release, or a quick release valve. You've heard me talk about, a tank valve and these types of things. I want to apologize a little bit in previous videos. Some of my terminology is pretty garbled up. I talk about valves, talk about tanks, and use terms interchangeably. But overall, if you look at the equivalent of one of these that would be made of metal, it is obviously much, much smaller. So effectively what we need to do is come up with a whole bunch of different designs that basically make up for the fact that we're dealing with plastics. And right away, if you start off on the video, and if you looked at the previous one, you could see that things are a little crunchier. And we'll talk about some of the reasons why, because obviously a plastic spring does not have the same properties as a metal spring. But yeah, so the important part is that manufacturing or building your own stuff using plastic is definitely available and easily accessible to everybody. Whereas doing everything out of metal and a metal 3D printer is actually orders of magnitude more expensive. So we're talking, for a few $100s for an entry level 3D printer that does a job. As you've seen from some of the videos already, there's a lot of design changes that need to be made to accommodate 3D printing. But as we're going to go through again in this video, you have to basically over-design everything to make up for the fact that plastic is a lot weaker than metal. So that being said, we're going to dive into this whole thing. I'm going to go through some of the design changes from the previous one. I'm going to explain the crunchiness. We're going to give this tank valve a go. I can get it sometimes to work on the previous, on the first go after I assemble it. But then after that, the new design does not work as well as the earlier design. And we're going to get into that, which in summary has to do with gear ratios. But overall, one of the interesting things from the last video, after working a little bit, is, like I said, everything is crunchy or sticky, and we're going to have to understand why that is, and run ahead and solve that. So moving right along, I'm just going to flip this guy over, and we're going to move right away with trying to use the new piece. So effectively what I've done is the gearing ratio is different in this overall head. The idea is that 1 millimeter of stroke turns into 3 millimeters of vertical displacement for the sleeve that actually pops this guy out. See previous videos if you want a better explanation. We're going to just try to build on it. So again, when I slide this in, the snapping right now is a lot cleaner. Part of that has to do with I don't have a nipple on this guy, so I don't have the ball valve, which we're going to see in this video. pushing back up on this, allowing it to come in, but for some reason it's actually crisp, and it's crispier on both sides, so I don't know why that is, but we can give it a go closer to the end of the video. And once again, if I turn around now and I push this guy, you can see that it actually is popped, which is good, and I'm hoping that I can actually now pull the piece out. So one of the effects of making the gear ratio, so the gear that is on the rack and pinion assembly is basically, the pinion is actually smaller, so therefore, you know, for me to get the same amount more displacement with a shorter stroke, the net result is I really got to wedge, really got to push hard on this guy. And as per previous videos, when I used to do this, I used to actually strip the gears. But now I'm actually not doing that. And if we can see, even just with one hand, I did not manage to actually release this guy. So overall, we have a problem. But at the end of the day, the problem starts off with the spring. So in order for me to be able to free this guy up, I actually have to disassemble it. So let's start off on that. And to do that, I'm going to put this guy on the ground. And in order for me to have two hands, I'm going to basically set up my makeshift cell phone holder, and here we go. So effectively now, you know, I used to take this off with a screwdriver, but if you just torque it a little bit, there's a bit of a wedge that comes in. I don't have long nails, but I can get my nail under there and I can open it up. And once again, if you've got this thing inside, you know, this is a little C-clamp, as I called it. It's a pin, it's angled at either end. You can see it very well now that it's in tank form here. Little eyes staring at you. Unfortunately, it's a visual artifact that we're not going to be able to get rid of unless the design gets changed completely. And if I torque this, I can get my nail under there. So, you know, on final pieces, you know, there's not going to be screwdriver scratch marks and everything else required. I could actually leave a a space here to get the fingernail behind, but the idea is you don't want to have to go into this. We want to get a final design. We want it to last thousands and thousands of usages before you got to replace the springs. You know, so the idea that it's flush and it doesn't pop out and everything else, I'm pretty happy with the way that's working right now. So when we grab this guy over here and we take it off, we're going to see now, because there's some pressure in here, so that's why everything kind of popped out. Again, this is the new design, and I'm going to put it on the ground once again, so I can take these things, kind of come out. And this new design is superior in a number of different ways, which we're going to go through. So I'm going to put this on the table, and again, to undo this thing, I'm going to come in. I could argue that if I was to use this guy over here with the pin and have the pressure of the ball pushing up, maybe it would work a little bit better. But once again, the gearing mechanism has to overcome the force of the spring for it to release. Again, see previous videos. So if we look down here at the bottom here, we can see our little ball, just barely, but it's there. And if I grab my screwdriver, we're going to see that the ball is spring loaded. And one of the important features in this video is that I'm using the new improved super duper springs. So when I printed them up and I first put them in, I was celebrating. Everything was working better than the last video. And then since the last video up until now, we're going to see that the performance has deteriorated considerably. So I'm just going to close these guys up so that basically this whole thing, alarms don't fall apart. We're going to flip it around. I'm going to disassemble. This is the original piece, or version, I called it version 4 in the last video. I could laugh at myself and at even my version numbers. But if we call this one version 4, we can turn around and use the new one and call it version 5 or version 4.1. But the best way of understanding the new parts is to see them via the differences. So here again, in the last video, we talked about this gap, whereas if I push this up, the buttons push out. That's still true. We're going to find out as a first order of business why things are as creaky as they are, and how come even this design works worse now than the previous design, despite the springs being so much better. So all of it has to do with I guess the elasticity and going over, I think it would be called the modulus of elasticity of the plastic when we make the springs. Basically, we're overworking the springs as opposed to deforming it in its elastic range where it rebounds. We're going beyond that and we're doing permanent deformation. So in order to do that, I need to do a better job at designing the length of the spring versus the size of the slots. But one of the differences is the slots where the springs are seated are now longer. So while that's dynamic, I'm going to basically leave it. I'm not going to play with the spring, or I haven't yet further played with the actual springs, but I'll show you what I've done a little bit later on. So we're going to put the tank on the ground, pull the wings out, and now we've got our second head. And if you can look at it from this perspective, there's actually hardly any difference whatsoever. So I'm going to put these two on my laptop cover, and one of the things that's new to this video is the tank, so I'm going to basically just continue to focus on that a little bit. So I'm going to pull this guy out, and I just want to talk about some of the changes. So once again, the new monster design is actually working out quite well, especially looking at this. If you look into the tank now, into the bottom of that tank, we're going to see the other one. And we're going to really get a good idea in terms of, you know, how well this works. At the end of the day, you can think about this as a bit of a drain plug to the exit. It's worth mentioning a few features of the actual tank design. One of the ones theoretically is that we don't have to have a quick release here. I can actually just put a cap on here and and be done. But the idea is you want to be able to connect to the top and the bottom of the tank. Pretty much, all the time, anytime. So what ends up happening is if I'm going to draw, the idea with the tanks is we're going to put different things in them, gases as well as liquids. So, water and air are the simple ones. And effectively, if you want something to come out, something has got to come in on the top. So, one of the attachments that you can expect would be a bleeder valve. And down over here, the tube valve that I did, and just a variety of different adapters to be able to take your fluids out. The idea with Octagon, and I've used SET as an acronym before, Space Ecotourism. The idea is we're not going to be using this to eat or to drink out of or anything like that, and that's not recommended anyways for a variety of different reasons. But once again, we're trying to see if we can do a whole bunch of things with plastic that used to be, or heretofore, is in the realm of metals. Okay, so we've got this tank, we've got this valve over here, we've got the ball, we've got another one over here, we've got the ball. We have a basic understanding of why that is. Don't believe me in terms of why we need two. In later videos, I'm actually going to put it all together, and then we're going to see how we can actually use it. And get a hold of me if you want to kind of understand a bit more what Octagon and this space ecotourism thing is all about. But one of the last things I'll mention right now is if you grab two of these guys and you put them back to back like this, you can actually interconnect the tanks. So if you fill the top tank, it'll automatically flow into the bottom tank. And effectively now what you're doing is you're taking a tank and you're allowing them to interconnect, changing the volume of this to virtually something infinite. So originally, the original design, if you recall, before I scaled it up to here, was smaller. So this was smaller, and the idea was to actually have a smaller tank, but I beefed everything up. And Octagon is named after the shape of this, which is an octagon. No big surprise there. And effectively, what I did is I scaled this tank up. So the smaller tank, which allowed this to be all the geometry of an octagon, was 2 liters. So I'm expecting this one to be at least 3 liters, or it could be as much as 4. Effectively, the outer dimensions of this are 20 by 20. I don't know why. I didn't originally design it just to be 20 by 20. but that's the maximum size pretty much of most 3D printers. And again, the idea of chaining the tanks together allows us to theoretically exceed, or we're not limited by a 3D printer anymore. Now we have infinite capacity. So in order for that to be true, obviously this has to be water and airtight, which is, we have a long ways to go before that's the case. And in addition to that, going back to some of the things that we're doing now, is that the way that this connects in with this latching mechanism has to be able to survive pressure. So how much pressure, I don't know. But one of the reasons that all of this is as beefy as it is that we do want it to survive as much pressure as possible when we get into the different fluids. So that's later on. And just to kind of give a preview, you know, the next step after this, obviously we have the tubes and the quick releases, which we have a preview of over here. And to move all of the fluids around, we need a pump. So basically a lot of this technology, as I've alluded to, I think in one video before, is going to allow us to be able to do a pump. So this ball valve was mentioned as one of the designs for the pump. And I talk about it now because I've actually done a lot of the design work. It's all CAD'd up, as I like to call it. And the next step would be to start printing it up. But first I got to get, you know, reality to agree with what I have on paper or in the design world. So we're going to swivel over here and go to our trusty dusty laptop, and I'm going to disassemble both of these individual valves or quick releases, and basically start explaining some of the differences. This is a quick release. These two are also quick releases, and this one does not have a valve, so I won't use the word valve. But this one definitely, well, the valve is actually on the other part. Strictly speaking, right, this is the valve part. That's a valve. So, yeah, so let's not get hung up too much on terminology, and let's basically see what's been done up until now and understand the differences, what has worked and what has not worked. So in both cases, you know, I got to press the button all the way in order to slide the assembly out, and we're going to start seeing some of those differences right away. This is the original one. This is version 4 from the last video. So it all comes out, well, it shouldn't all come out, but it comes out, and you know, it is what it is. It's a little bit messy in the way that it's coming out. And again, we have at the bottom here, the seat for the first button and springs is actually at the bottom. So I'm going to put this in, I'm going to put the springs back in, and I'm going to explain kind of what's gone on with the springs. So if I show the springs, these are my monster springs. I've thrown out the thinner ones. In the previous video, I stated that I made a video. I'm making videos so that I can throw out earlier versions and not keep accumulating, you know, designs that are effectively defunct. But this spring overall, you could see that it's actually, I'm going to say, done or spent. Okay, so you know, ideally when these are brand new, all of the lines that are vertical in this scene, in terms of what I'm showing right now, they're vertical and they're parallel. And what's happened now through repeated use and through, I'm going to call it, again, exceeding the elastic range and permanently deforming this guy, which is what's happened, is the problem. So when I made this thicker, I actually made it a bit longer. And it's really, really interesting in that, because when I stick this guy in here, and hopefully we'll be able to see down to the bottom here, so you can see what I'm talking about. When I push this button in now, I don't know if you can see it. I'm going to use my screwdriver as a pointer. Okay. But there's a little gap here. Okay. And I cannot compress the spring anymore. Now, and when I'm forcing it like I am before, I'm actually assisting in permanently deforming this overall spring. And that just in itself, never mind the new design, explains why when I printed these new springs, you know, and this was brand new, it worked fantastic. And, you know, the springs were very strong because I was going to the minimum. But through repeated use now, this button doesn't even bounce back up. You can see there's a gap here. So I can't get the button with the spring to come all the way back up. There is a gap there. Okay, so that's, and what I need to do again is lengthen the design run and make sure that I don't compress the spring to its maximum capability. Okay, so that's that bottom piece over here. I'm going to continue the disassembly. We're going to put the case over on the back side. And again, previous videos, I get into how this whole thing works. So one of the nice part about this design is that I have all of my gears in a cassette, I'm going to call it. So this is a little piece. I can theoretically change the whole geometry of everything, and it works great. You know, from a design iteration perspective, this is fantastic. But if you recall, one of the reasons I have an interface over here, I have a gap down at the bottom. I got 1, 2, I got this interface over here, 3, and then on the top over here in the back, 4. So all of those tolerances are not, you know, I can't just say in CAD that, you know, I have to assume 0.2 to 0.4 millimeters is going to be occupied by the fact that when you end a piece, you know, the two contacts are not there. This is just why I'm overusing the word tolerance all the time. So the nice part about this cassette, obviously, is the gears are all in here. I'm settled down pretty much on this design. That is, I'm pretty sure I can get it up and running and, you know, kind of reaching points of diminishing returns. So I'm going to pull out this gear because this is the real main difference between this version and the previous version. Okay, and I just want to basically touch on this part over here. So this overall design change from this one is actually, you know, makes all the difference in the world. So earlier I was talking about how, you know, we have to basically relearn how to design everything in plastic, or from a societal perspective, society has never designed gears in plastic, right? Because metal was invented first and all our gears are made of metal. Why the hell would you make a gear out of an inferior material? And that's what Octagon set is all about from a philosophical perspective, or a, you know, 10,000 foot view perspective. But if I look at just the little bit of a difference from, you know, that this makes, or sorry, the little bit of design change that's in this guy over this guy, I cannot shear this gear. You've seen me force at the beginning of the video to basically push the button, and, you know, I would have actually popped the gear, or I would have deformed it like I've done this one. So, you know, what is it? It's just a little cone at the end of the day that is, you know, it's a fraction of a millimeter, and I'm not even, you know, doing the full outside circumference. So the gear is still mesh in that it doesn't interfere with its gear workings. But I mentioned it in a previous video, when you do gears, when you're 3D printing, you want to cap them in one way, shape, or the other. So again, the fact that this is a flat surface, a couple of things, you know, obviously this is not gonna grip and cause friction, but I had that solved. Just the amount of strength that this added is actually incredible. So again, now I'm not afraid anymore to reef on gears. But that being said, you know, let's look at some failures. So I stripped these gears, and one of the things that I thought was really interesting is I actually sheared one. So, you know, if you look at large gear and shaft assemblies in 3D printing, they recommend that you print the gear, you know, in one orientation in the printer bed this way, and you print the shaft actually horizontally so it has more strength. And I'm getting into this because it has an effect on one of the elements of this design that is making it creaky, that we may or may not have to solve. I'm not sure, but I'll talk a little bit about it a little later on. Okay, so again, I promised that we go through the scrap pile, and so we did. Half of it anyways, there's a little bit more to go. So I'm going to leave the rest of this sandwich over here and put it over to the side. So once again, you know, these gears here are actually the same from our version 4 to our version 4.1 or version 5. Haven't quite decided yet. So I'm going to stick this guy over here and move this guy over. So when I was talking about the shaft and the orientation, you could see that when I printed this, especially this detail right over there, is not, quite frankly, it's a horrible finish. But because this is a piece that is both in tension as well as in compression, if it's just in compression, printing it this way would have been fine and I would have got a nice finish and it would have looked good. But now, because this is actually being pulled, right? The gears are pushing and pulling. I actually printed it this way. Now, maybe I can try printing it this way and see if the nice finish ends some of the creaking. But the other reason for that as well is that I want to make sure that I print the gears, right, in an orientation that maximizes their strength. So once again, these gears are printed, I print these guys this way, I don't print them that way, okay, for strength. And I can go back, I'm going to show some bolts when I talk about this thing, and you know, the same kind of applies over there. So yeah, so this guy is causing me problems. I might have to lengthen the actual rack part so that I can, I guess, eliminate, you know, am I going beyond, like some of the popping, you know, going beyond beginning or the end on the first gear. As you've seen from previous videos, you know, I'm pretty minimalist in the design. That's because ultimately the goal of all this is to make the plastic that we use for the 3D printing. So even the plastic is, you know, is going to be a bit of a scarce commodity. So yeah, so we don't want to make things any bigger than we have to. We don't have to use any more materials that we have to. So that being said, put the phone back down, move over here, and we'll start to disassemble this bad boy. So one of the things we're going to see is that I have first thing I have is a spacer. So again, the design is fully symmetrical, and I'll pull out the button. And the first thing you're going to notice is the button sleeve, as I think what I called it in the files, is basically, you know, it's just that. It's just a case and nothing else. Is that a good idea? I don't know. This one has it on the bottom. I had to do that for one very specific reason, in that now if we look at the cassette that is left over, we have both button pieces, and once again the design is completely symmetrical. Okay, so you know, we could see over here, to go back to kind of the same story as before, I have the new design. So I basically channeled the spring all the way down to here, and these are touching together. The spring is longer, and you could see over here I'm actually not maxing out on the springs. I'm not going beyond its deformation range, or I'm not crunching it beyond its maximum design compression. So that's the mechanical part, but if I look at it from a materials perspective, yes. So what I need to do is I either need to get rid of one of these things, and I'm going to show you the use of these heftier springs in the actual valve, okay? And the other one over here is I do believe I have a little bit more range. So one of the things to do is to actually, you know, print another one of these guys, stretch this out. But you've seen in previous videos that, you know, I don't want this to start to fall apart, but I want to give myself the maximum amount of strain. And the idea, that this might sound counterintuitive, less linkages or less S's or bumps or doubling over the spring might actually be better, so that I never, you know, we stay within the elastic property of the spring. So there's a lot of iterations to do over here. That's probably one of the next things to do, but again, try to get all other elements of the design kind of settled down. Okay, so now once again, the nice part about this guy is that it's perfectly symmetrical. Okay, so you can see I'm still using, this is a 0.2 millimeter tolerance, whereas my average tolerances are 0.4. And you could see over here, I talked about this in the last video, I added this actual rail in order to stabilize the button in this axis. But 0.4 is still quite a bit. And one of the things that this has had the effect of is that the assembly is a hell of a lot easier. But because the previous version actually works better than this one, I'm going to say, you know, designing for functionality needs to be the first thing, and then designing for manufacturability needs to be something afterwards. So, got to get one, you know, got to build your first floor of your house before the second. Got to get the first thing kind of nailed down before the second one. So, but overall, having this as an overall package is a lot better. But obviously, I'm losing some modularity in that, you know, I got to reprint this whole thing if I want to change the gear seatings. So, pull this out, and you know they're exactly the same. And once again, with the springs, the beefier springs, I think I actually may fatigue these guys in the previous design before I put them in here. But overall, these are beefier springs and they do work great, but again, they just don't last. So I'm going to put this over here. I'm going to crack this guy open a little bit later on. What I want to show firsthand is basically a comparison between the button piece on the previous one and the button piece on the current one. So they're both exactly the same on the new design, and this is the old design versus the new design. So effectively what I've done is I've changed the gear ratio. I've gone back to the smaller one as I talked about before, and that's the old one, and this is the new one. And you can see here there's actually a bit of a hairline difference there because I actually had to play with the tolerances. So to go through the whole backlog of failed prints, so this is version 4. This is actually, I'll call this as version 5.3, and I might actually go to 5.4. But if we look over here, I actually have, you know, this will be version 5.1, this will be version 5.2, and this will be version 5.3. So I'm going to grab one of each of them, and I'm going to bring them here, and we're going to look at them one next to the other, if we can. I don't want to get them too confused, because so you can probably see it best looking at over here. So effectively what I've done, and my standard tolerances is 0.4, so I just increased the height by 0.4 millimeters. So I got all excited about having solved all the design problems of the previous version, and I put it together, and basically it didn't work. And what was going on is that the tolerance between this and the pinion gear was too high. So what I did is I reprinted. This would be, you know, version 5.1, version 5.2, and this guy here is 0.4 millimeters taller than this guy over here. I don't know if you can see it in the camera, but it actually goes, you know, down. And then from there, I put this together, and it was a bit better, but still wasn't getting enough traction. I still wasn't getting any skipping, so I basically printed another version, called 5.3, that basically is 0.4 millimeters higher once again. Now you can see that I actually got, I'm assuming, some skipping when I was actually pushing the buttons, trying to get the dowel out, and it didn't quite work. So, you know, there's probably room for this to actually increase by another 0.4. But basically, the pressure problem, I believe, is one of the more significant problems. So I think it's more important to solve that before we go on. And obviously the creakiness, you know, as it affects this design as well, is something that we have to solve, and that's going back to the spring issue. Okay, so that basically are the various button designs that we've gone through. And overall, you know, one of the things, these rails here are really worth the while in that, you know, it makes sure that the actual gear is pushing up against the, the rack is actually pushing up against the gear, the pinion. And again, you know, it doesn't necessarily solve the rocking problem. And one of the things that this has is it actually increases the friction problem. So maybe some of the additional creakiness has to do with the extra friction that is introduced by this. I doubt it, but again, we're increasing the rubbing surface area when we do this, so therefore increasing friction. So I'm going to put these buttons back into the waste pile, and we're going to continue on basically looking at this piece over here. So again, you know, the cassette or the two pieces are actually bigger. So instead of, I basically joined the pieces that were there before. The inner workings of this thing is pretty much the same. You can see maybe from before I actually had to cut out a few pieces. That's actually a design error. Now that the gears are so much smaller and the rack is so much higher, I fixed this piece, but I didn't fix that one. But that doesn't make much of a difference. You know, these gears overall, once again, are exactly the same as in the previous design. And the main difference of this design of version 5 from version 4 is this piece over here. So what we've done is we've moved from you know, having a large diameter gear to a small diameter gear. So in the previous video I talked about this gear here and the ratio between, you know, this guy and this guy. Now for the purpose of that explanation, it was actually fine. But in terms of this video, or in terms of solving problems moving forward, more important is what we need to be talking about is the difference between the gear ratio of this guy and the gear ratio of this guy as the two things that are actually delivering mechanical force. Because this one and this one are exactly the same, its effect in the overall equation or in the linkage is not what's actually really important. So to bring this, you know, why is this explanation important, is it kind of brings to bear, I guess, the pressure problem. So this might be 30% bigger than that one, but this is only 10 or 20% bigger than this guy. So what ends up happening is that this guy over here is way smaller than 30% of this one. So again, I am, for, you know, a little bit of stroke, I am getting a maximum amount of displacement. I thought that that was required, you know, to soak up some of the button sloppiness, but I think we've overcooked it. So the ideal final design, I believe, is between this guy and this guy. And the new design allows me to play with that because I can actually just now print new ones of these gears. I have to print a new button every time I do that, but I can play around. So one of the things that may be affecting the stickiness is the number of teeth of this guy. So once again, I've said it before, but I can't stop saying it again. We know we have to cap our gears when we're 3D printing, or that's, you know, if we want to get good performance. So this one here is fully enclosed. There's enough of a tolerance so that the rack slides in between here without too many problems, okay? And the same is true with this guy over here. You know, the rack gets in here, and even if this is a lot smaller diameter than this guy, I'm still getting the confinement from end to end that is important in making sure that this gear doesn't torque. So I don't think the torquing is the problem necessarily, but a larger gear will, this one will enjoy less torque than that one. You know, torque being a motion, you know, in this direction and that direction, because we're using angle gears. So yeah, so happy with this guy. Next changes would be this diameter a bit bigger between this guy and this guy, and as a next course of action, we could increase the number of teeth on this guy or change the diameter of this guy to a smaller one. So why don't I want to do that? If I do that, obviously the distance between, if this diameter changes, I got to reprint this guy, change the distance between, you know, these guys have got to stick out more if I make this guy smaller. Hopefully it doesn't get to that, but they are design options. And obviously if I start to change some of this geometry, you know, I'd have to reprint these whole seats because this has got a fixed distance between the center of rotation of this and the sidewall. So again, lots of things to try, but one of the obvious things that I basically don't want to do, or didn't want to do, but I'll try it, is actually put grease in here. So I think I'm just going to grab some petroleum jelly, throw it in there, see if it makes up, you know, stops some of the creakiness. If you look at it, I don't know if petroleum jelly will basically degrade the plastic in accelerated fashion. There's lithium grease as an alternative to that, but overall what we're looking at with that is when we're adding a lot of pressure, it's a fluids dynamic problem in terms, so we're actually adding, the fluid actually takes up some of the pressure and smooths out the translation of the gears, so it's not just mechanical on mechanical. So because Tinkercad actually idealizes all of the shape, they're not perfect spheres, there is still a circle is a whole bunch of different little segments. So I think overall there's some things to do in there. In future videos we'll go through all the various changes, but effectively the difference between the current version 5.3 and version 4 over here is the difference in this gear ratio. Reducing the size this dramatically was not a good idea, but all of the other design changes were definitely worthwhile. So while we're here, I just wanted to quickly mention, because I have this piece in hand, one of the changes that was made in the previous video was this overall. So we basically reduced, there's a bit of a step on this guy. So let me just put this piece down. There is a step. This piece here is thinner than that piece here, and it actually steps up. That turned out to be a bad idea because it created some wobble. So once again, the play that was introduced, so this is 1.8 mils thick, this is 2 millimeters thick, and this has gone from 2 to 2.4. In the latest version, I've gotten rid of that step, so this is back to 2, this is still 2.4, and obviously this is still 2, and that got rid of the wobble. So now that I think about it, it's probably one of the reasons why the click is a lot more crisp, i.e. The last version kind of sprung in smoother and sprung out smoother. That's probably one of the reasons, because this is stiffer. But the play that was introduced in here was a little bit too much. So just wanted to cover that because this is part of the graveyard. Okay, so we got this explained. We basically got the overall sandwich explained, so we can put that back over here. What I wanted to basically do is touch on a few items of the actual valve. Okay, so if we look at the valve piece itself, one of the major changes, like I mentioned before, was actually there's a bigger spacing on this side. So I'm going to basically leave you right there, and what I'm going to do is grab from the graveyard is the previous version. So what ended up happening is we have the first O-ring is actually very close to here, and because of the tolerance or the space that we have between here and here, I couldn't make that work. So what ends up happening is if I take these O-rings over here, which we're going to work with shortly, and we put it on this guy, and then I stick it on the tank, what's going to happen is that it's not going to fit. So if you look at the new design, and we're going to put the springs in, or the seals in shortly, you can see that it actually steps back and steps in so that we have that right tolerance over there. And I couldn't make that work geometrically without that. So if we put these two pieces next to each other, we're going to see that in the earlier version, from here, right, this actually goes down. Okay. So what I've had to do overall in here is that I've actually got to come in, and it goes down way steeper now because we're starting off from much higher. So we're going to have a look again, like I mentioned or threatened earlier in the video. We're going to look at the bottom of the tank, but while we're here, I just wanted to show the overall O-rings. So again, the outer dimension of this guy over here is limited by the cap, and if I put this guy down, we're going to see how this fits in overall. Now, I use the same tolerances or the same dimension difference between this outer distance and the actual nominal diameter of the ring, the difference between the two is the same as this, where this one here, it's stretched out and it works out nicely, but here, these ones here are way too loose. So again, we're not going to do any water testing, but I'm going to have to reprint these. But the idea was just to show that with this guy over here, you know, I can't get a good seal, but with the new guy now I actually can. So getting a seal between this piece and the inside here is actually quite important, but just as important, you know, before we can start putting any fluids in our tank, we actually have to get this seal here right overall. So I want to talk about that a little bit because, you know, we talk a lot about tolerances, we talk a lot about using 3D printing, you know, for things, applications that were reserved to metal. Now we're looking in at the bottom of the tank and we can see kind of what this looks like. So I'm pretty happy with that, because if you look at the slots that I was putting my screwdriver in previously, you can see that it forms pretty much a drain. And I'm pretty happy with how flush that is, or how much it doesn't stick into the tank. So before, when I had the previous design that was smaller, and I had some earlier kind of conceptual designs, this whole mechanism, and specifically the springs, were actually coming in almost to the center of the tank. So pretty much the whole tank was filled with that valving mechanism. So being able to keep a low profile like that is something that I'm pretty happy about. But again, given all the problems that we're having with the springs, or what we will need to do to the springs to have it work properly, we probably want to, that's probably going to have to change. The springs are going to have to stick in a little bit more. So to finish up the design on that, I do want to talk about the springs. So I'm going to take this guy off. By making this guy taller, I actually had to move this slot up. You know, so now we have a different cap. But again, when I pop this guy off and I take these out, we talked about exceeding the elastic range of the spring. So here we've got the basket coming out. That hasn't changed. We got our ball. See you later. Okay, and here the important part here is mentioning once again what's going on with the springs. So in this case here, I've actually I've cut off the last piece of the spring. So if this guy is pointing up, you know, the last one actually points up. On the springs are the same for the spring back for the button as well as for the basket. And if we look again, you know, we've exceeded the elastic range of the actual springs. This guy here is permanently deformed. Now I've done a better job with this design in that when we actually put the spring in here, okay, it sticks out when it's brand new, okay, and we're compressing it. We're compressing it too much, most likely. But what ends up happening is that the basket isn't actually, the basket bottoms out here lower, right? That's its maximum range, but the ball does not exceed the maximum range of the spring, okay? So that's a good job, but if I look at it, you know, if the spring is 100% of its length is when it comes off the 3D printer, you know, we probably have to compress it down to 90, and we're probably compressing it down to, you know, 85. And then its maximum physical compression, which is pretty much where it is now, if this is 70%, we should probably never exceed 80. Okay, so what's going on now is that I am still, you know, this is still compressing itself down to 72 or whatever, where we would have to only compress it down to 80. Now I can shorten the number of links in the spring, but because the elastic range is so small, I have to increase the number of runs as much as I can, and we have to lengthen these channels. So what do we want to do in terms of lengthening the channels? Okay, so if we look at where these channels are on this side and I flip it over, okay, right now the channels are actually, ultimately the channels want to come into these two pieces over here. I can't come into these two pieces because, you know, There's a slot required to put in these pins, but on these two guys here right now, this is bottoming out, you know, just a little bit coming into here. Now, making it bottom out further is a good idea, but one of the reasons that I don't want to do it is this whole idea of water resistivity. So here we're going to get into some of the basics of some of the design, some of the fundamentals of the design. Overall, if you look at 3D printing, people are going to say 3D prints are not watertight. Okay, so now obviously if you 3D print something and you put water and water leaks out, you basically, yeah, it's not watertight. But there are two settings that you can play with that basically will improve the water tightness of your 3D printing. One of them is infill. This is a pretty big piece by 3D printing standards. Again, we want to be a little bit, we do not want to consume a lot of plastic because, again, we want to make our own plastic, and you know, plastic will be somewhat of a precious commodity to a certain extent. And probably the biggest factor for me is time. It takes a hell of a lot longer for this to print at 100% infill than the 40% infill that I'm actually using. So when we talk about 3D printing, what we're doing now is that we've got a 0.4 millimeter nozzle. We've got two runs, you know, so 0.4 times 2 is 0.8 as the actual wall thickness this way. We've got a 0.2 millimeter thickness. I can actually increase it to 1.2 or to 0.12, less to give myself more resolution. But at the end of the day, that'll just make the prints take longer. And what we have over here is we've got 4 layers, and inside of that, it's effectively a sponge. It's a honeycomb. It's a grid, and that grid obviously is very porous. So if we push through the outer walls, you know, water is going to get in it. This thing's going to get waterlogged and everything else. 100% infill will fix that, but also the second parameter that I haven't used yet is extrusion settings. So the 3D printing, which is as always working over here, is like a hot glue gun. So what we want to do is we want to increase the pressure through the nozzle so that more filament comes out in the same unit of time. And what that'll do is it'll squirt and squeeze, you know, next to the piece next to it, and that'll make it more watertight. So over here on this specific tube length, I have this printed 100% infill always, and then I did 100% extrusion of this 2PU filament, and then 120, and the pressure that I can put through and the water tightness has actually increased significantly. Okay, so I got a couple of little videos showing me, you know, blowing in one of the ends of these in a bowl of water that basically you know, can be added as a reference. But overall, the extrusion settings can be played with. So what happens now with infill? Infill takes you know, more time. Obviously consumes more printing filament, and then from there, but that doesn't change necessarily the design parameters. But when I start to play with extrusion, this whole idea of tolerances is going to change all over again. So what you want to be able to do is kind of minimize, for all these reasons, the amount of parts that you have that need to be watertight. So very specifically in this piece, these O-rings over here on that dowel, okay, seed in over here. And then this is the entry to our tank where the ball is. So this is the only area that would actually have to be waterproof. Okay, so minimizing the amount of area that has to be waterproof is important. Now, if I do 100% infill on this guy and increase the extrusion, I'm actually changing the tolerances of everything. So maybe I need to modularize the design in that I need to introduce another piece. I'm not quite ready for that yet. But overall, you know, it explains a little bit the design in terms of why everything is very compressed. We're trying to minimize the amount of areas that do need to be waterproof, recognizing the 3D having waterproof and for, you know, gases, high pressure 3D prints is going to be problematic. But this said, over here now, you know, this guy will be able to be put into our tank, you know, with a certain amount of water tightness. Okay, and you know, we're ready to do some of those tests, except that, you know, I got to print these guys so that they're a little bit tighter. So with that said, I want to move the watertight discussion to the actual tank. And again, I do not expect this tank to be neither watertight or airtight. So first of all, let's talk about watertight. How watertight does this tank need to be? So we're going to assume that we want it 100% watertight. But that's not necessarily true. It's the same thing with metals. Your expectations on how a spring works, what the size of a quick release is, you know, for pneumatic couplers, which is effectively what these tank valves are. You know, you have an expectation of size of metal. Why would you want to use one that is a lot bigger, you know, and maybe doesn't last as long? Well, the answer lies in the plastics, in that if we can 3D print, if we can make our own filament from air, which is what we're doing in Octagon, then we can actually bypass mining and the use of metals. So if you think plastics are complicated to make, you know, metals, if you're landing on Mars, bringing a 3D printer and processing the air to make your own plastic is going to be a hell of a lot easier than flying over a whole fleet of mining machines. So what we then have to do is just live with the we have to live with the shortcomings of the material that we're using, in this case plastic, and in this case watertight. So how watertight does this need to be? It has to be you know, watertight enough to hold the fluid enough so that we can basically use it. And again, the use case that we're looking for is to make plastic. So what do we need to make plastic? That's going to be the topic of a whole video on itself, or, you know, we'll make it available, or it is available in other formats. But this tank over here, in terms of its water tightness, I want to go through and kind of explain a few artifacts in this, which will obviously affect its water tightness. So the first we're going to see is, as I'm talking here, we can see that there's these diamond artifacts, you know, on the side of the tank. So they're there on the angle surfaces, right, or the tapered surfaces, as well as on the big flat surfaces. So when we get to this point over here, the wall thickness is only the 0.8 millimeters thick that I was talking about before. So when we were looking inside the tank, you can probably see that the tank is actually a perfect sphere, whereas the outside is an octagon. So what we have in these corners over here, we actually have quite a bit of space, which hopefully is what's going to give us the strength that's required in this tank. But in order for this tank, it took 3 days to print, to basically, you know, take as little as that the wall thickness, I minimize it as much as possible, and I'm using only 20% infill. So we're going to have a look to see how that resists, and once again we can start turning around now and playing with 100% infill, which will only really affect the corners and probably only increase our strength. Increase the wall thickness so that if I go any thicker, these diamond artifacts will go away. But also, probably more important, is that we'll need to improve or increase the extrusion, okay? But in the meantime, we can still do some basic water tests in here, and basically, hopefully, it's going to give us a result. You know, a leaky result is still good enough. And again, you know, chemically we'll have to see whether or not we actually, how this will resist chemical reactions with the actual fluids that we want to put through this thing. So yeah, so that's a little bit about the tank external parts of the tank. We've actually gone through, you know, the tank valve, you know, and where we're at with the its waterproofing and everything else. So to wrap up this first video about the tube, I have to basically reassemble this whole mess that I've now created throughout this video. So let me do that, and then we'll come back and show this guy on the tank. Okay, so sometime later we have tank assembled once again. So this is a pretty long video, you know, with the tank coming in, you know, the diamond version or the thin version of the tank. I'm pretty excited about everything coming together and starting to look like something that can do something. Thanks for your attention. We'll talk to you soon.